Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to talk about concepts associated with torque. So let's get going. There's a lot to talk about here. So, first of all, it's good to understand the definitions of everything. Now, it might not have been stressed so much in your classes up to this point, but it's important that you know that there's something that's going on in physics. Okay, and what it is that we define things in physics two ways always. In physics, you're always going to have a definition that you could go on the back of your book in the glossary and read, and it's going to tell you like the science, what I call the science definition of torque, but or of an idea in physics, or not torque, but torque too. And you'll also be able to find a mathematics definition for everything in physics. So again, here in physics, we always have science definitions and mathematical definitions. And it probably hasn't been stressed so much to you because it wasn't so important to know up to this point, but from here on out, it's going to be super crucial that you understand that idea. Okay, because we can define torque two different ways, and those definitions define how we're going to solve it and use it as well. All right, so first of all, the thing that you need to know that's super important is that the science definition is that torque itself is how effective a force is at making something spin or rotate. Okay, so you don't have torque without force, but torque is just measuring, right? Torque is telling us how, if I apply a certain amount of force, how much spin that's going to have, right? Right, so this can have spin. If I apply force to it, geez, that's not working very well, right? It can spin. I can give it spin, right? I can give it torque by the push, right? So based off how effective that force is, right, I can apply that same force, and you can see as I get further away from the axis of rotation, that force becomes more effective at spinning the thing. So you can't have torque without force, all right? So we look at torque as if it's its own force, a twisting force is what we say, but it actually isn't like a force itself. It's just how effective a certain force is at making something spin. And keep in mind, when we say force in here, we've said that with every definition, okay, in physics. But remember, forces can be individual things like normal force, friction, a push, all those forces. I can go through a weight, right? So when we say how effective a force is, it can be all that. How effective a force is at making, or your weight is at making something spin. How effective friction is making something spin, right? We can say all that in there, but we're being general right now, but that's what should be in your head, all right, when we say those things, all right? So that's what torque is, right? And we can see by the mathematical definition exactly how it works, where we can see how efficient, how effective that force can be. How do we know when that force is really effective, and how do we know when that force isn't very effective, right? So when we look at the definition, the mathematical definition of torque, we see that it's the distance, so there's this r, right, which is the distance from the axis of rotation. That's what r is, right? In all our pictures, r is going to be the distance from the axis of rotation to the applied force. I didn't write that in there. It just says distance from axis of rotation, but it should say to applied force. Okay? Because that's what that is. That's what R is. Distance from axis of rotation to applied force. And then F, it's very specific here. The force for torque is always going to be the perpendicular force, okay, to the surface area, right? So like, let's imagine this is a door, right? A door swings like this. I push a door, it swings open like this. The door's closed, I open the door like this, I walk through, and then the door closes, okay? So, perpendicular to the surface area means this, right? This is the surface area. If the door swings on, this is the hinges where my hand is, right? So the door swings like this. If I push on the door, if I apply force towards the hinge, that doesn't make the door swing, does it? Right? When you push on the door, the hinge is here, and you push towards the hinge, it doesn't make the door swing. What makes the door swing? When you push at a 90-degree angle to the hinges, right? That's what makes the door swing open, right? So that's what we call the surface area, right? The surface area of an object, okay? This isn't the surface area. You push on this, you're not going to get any torque. But you push on the surface area, you're going to get some spin, okay? And based off how close you are to the axis of rotation, right, that's what this saying is going to dictate how much torque you have. So the furthest away from the axis of rotation, right, we say that we have max torque. That's where torque is totally maxed out, where the force is perpendicular to the surface area, right, perpendicular, right, and this furthest away, this is the axis of rotation, furthest away from axis of rotation. So it's perpendicular, can you see it? And then it's furthest away from the axis of rotation. That's how we know the torque will be max for that system. That's how we know, now keep in mind what we're saying there, that's how we know the force will be most effective at making the object spin. Okay, so when we say there's max torque, we're saying, yeah, max torque. You gotta know what that means. It's how, that's when the force is the most effective at making an object spin. You need to know that because you can rank torque. If you had a lot of different forces on one object, you can rank them. You can rank them. You know which ones are going to be the largest. The one that's furthest away from axis of rotation and perpendicular is going to be max torque, and that's what it says. Max torque is when the force is applied furthest from axis of rotation and perpendicular to the surface area. Okay? And what do we mean when we say that? That's just when the force that you're applying becomes the most effective. That's what max torque means. Max torque means when the force you're applying is going to become the most effective. All right? And again, we can see that from this equation because the force is about the perpendicular force and the distance from axis of rotation, right? The larger number this is and the larger number this is, the larger the torque's going to be, right? That's what we're saying. So that's how you want to read this equation. We can also see from this equation when torque is zero, right? Where we'll have zero torque, right? And there's two places for that. We see that we have zero torque, and I have two pictures right here for it. Okay, we have zero torque. I'm sorry, this is max torque right here. But we have zero torque. This is my picture for zero torque. When the force is applied to the axis of rotation. So if you have the force that's applied directly to the axis of rotation, the torque is zero. Why? Why? You should know why. Why is the torque zero? Force applied to the axis. Torque is going to be zero. Why? Because R is zero. R is the distance from the axis of rotation to applied force. The force is right there, right? The distance to it, it sits right on top of it. So the distance to it is zero. There's no distance. The F sits right on top of it. So R is zero in here. That means torque is going to be zero, okay? And that's what we're saying here. When the force is applied to the axis of rotation or applied through the axis of rotation, R is zero in this equation, okay? And so torque is zero. Now this one's a little bit hard to see, right? But we can look at it. The force applied through the axis of rotation, or another way to think about it is along the plane, right? And that's, again, thinking about it like this. Like if this is a door that swings on hinges, right? Like this. If I push on the door this way, it's not going to swing this way if I push in on the door, right? The door swings this way, but I push this way on the door. That doesn't make it swing. I have to push this way on the door to make it swing open, right? And that's what we're saying. So when the force is applied along the plane, so that's applied along the plane, that's one way to think about it, or through the axis of rotation, because when I press on this, the force is pointing this way and it's going through the axis of rotation, which is what this is trying to show you. When we talk about the line of action later, you'll see we extend the force to see what the force is doing. We do it right here, right? And when we extend this line, or the force line, we see it goes right through the axis of rotation. And if it goes right through the axis of rotation, R is zero again, so torque is zero, okay? So let's just review, because this is important. Torque is how effective a force is at making something spin. We know max torque, or the force that you're applying to an object, is going to give the thing the most spin, or going to be the most effective at making the thing spin, when it's the furthest away from axis of rotation and perpendicular to the surface area, right? We also know torque's going to be zero from our mathematical definition of torque, okay, when the force is either applied to the axis of rotation or applied through the axis of rotation, okay? Both those cases, torque will be zero, R will be zero for both those cases, whether it's going through or on the axis of rotation, all right? So we know that, which means the force won't be effective at all at making it twist. That's what that means when we say torque is zero, right? So This next step right here is we want to now find torque, because sometimes the force isn't going to be directly perpendicular like we want it, right? So when the force is at an angle, right, we still want to be able to find torque, right? So the way we do that is we have to first find the components of the force, right? So when we look at the force, right, we see the force is applied this way, right? It's not totally perpendicular. Perpendicular would be if the force is directed straight down, right, like this one. This is max torque right here, right? This is furthest away. This is at an angle, right? So we know it's going to have components. So we draw the components, right? Here's the x component of the force, and here's the y component of the force, right? And then we write those values of the components, so we know that this vector right here is adjacent to the angle, so that's f cosine theta, and we know this vector right here is opposite of the angle, so it's f sine theta, right? And then we write our equations. We can write our equations for two of these, but we already kind of know what to look at, right? We know that torque only has to do with the perpendicular force, right? This is our plane, right? If you can't see it, let me make sure it's darker. Looks like it kind of faded, right? This is our object that things are being applied to, right? So we see that the y component here, right? This is the x component, is perpendicular to the surface, where the x component of the force is what? Along the plane or through the axis of rotation, right? If you can't see that, let me make that bigger. So make sure you can see that. This is the direction of the y vector, the x vector, right? So it's this way. So it's along the plane or through the axis of rotation. So we know that if we were to write a torque equation for this x, we would start with torque equals to r, and then we'd write F, right? The next is the F. We know it's not perpendicular, but just let's say that we would. We'd write it in there, but we know F cosine theta, right, is gonna, we know oh, I'm sorry, not F cosine theta. I wrote the wrong thing there. Look at that. Don't want to confuse you. We know that here, even though F cosine theta is gonna exist, okay, that's gonna be a value. R is gonna be 0. And if r is 0 for the x component of the force, then torque is going to be 0 for the x component, or the torque, right, for the x component. The x component of the force for torque will be 0 because r is 0 for that. So when we come over here and look at the y component, I have it written over here, we see that the torque for the y component, right, if we start with this equation, is going to be r, right, and then we see that the f is going to be f sine theta. Well, we see that the r here is going to be a certain distance. It's not 0, right? It's going to be, now I know I have it written over here, but keep in mind this, since the original force is right here, this is actually sitting right here. Remember, we can move this around, but I think you can see it. But keep in mind that force is actually right there, right? These are the same vector. That's just how we got the component of it, but it's over here, right? So we know that the force, right, this vector right here that sits right here, it's going to have a certain r, and it's going to be perpendicular, right? So this is the way that we write torque using the perpendicular force. You have to know how to do this, okay? So it's important that you understand what I did here. That's why I want to go through it one more time. Okay, so if you have to find torque using the perpendicular force, which is using the definition of torque, and it's also proving the definition of torque, because we can see that when the force is at an angle, the x component of the force in terms of torque, or the x component of torque is going to be 0 because the r is going to be 0, right? We know this, okay? And so since that's going to be 0, we know that the only force the only component from this force that's doing or is going to give some torque, or is going to be effective at spinning this object, is going to come from the y. We can see it here, right? It's easy to see here because we're like, oh, it's the perpendicular, that's perpendicular. Yeah, that makes sense. But we want to prove it, right? And we can prove it by looking at the components of the force, seeing which component of the force is going to be perpendicular to the surface. So keep in mind, depending on the angle, sometimes f cosine theta is the one pointing down, okay? Because the angle dictates it. So don't always think that it's going to be written f or rf sine theta if you're using the component of force to write torque. Sometimes it can be rf cosine theta based off where the angle is at, okay? Since the y component, or the perpendicular component of the force, is opposite of the angle, that's why it's F sine theta, right? And that's the perpendicular force, right, in terms of torque, okay? So again, in order to find torque using the perpendicular force, the first thing you have to do, get the components of the force, okay? The second thing you do is look for the component that's perpendicular. I did this extra work over here with the X, all this stuff here, so that you could see that it's 0. You don't need to do this. What you should do is look at that picture after you draw the components and say which one of these components is perpendicular to the, right? This is our surface. So which one is going to be perpendicular? We're pointing like this, right? Which one of these forces? This one is not perpendicular. The X is along the plane, right? So we see the only perpendicular is the Y. So we just write the torque equation off of that, right? Where this sign, by the way, we're going to talk about it here next. It's just coming from the way this force would make it rotate. So since this force is pointing down, this object would want to rotate in a clockwise fashion, which means it's negative. Okay, that's where that sign's coming from. We'll talk about it in a second. But the equation, again, once you get the component of the force that's perpendicular to the surface area, you can just write the equation by first writing R, where R is going to be the distance to that component. Now keep in mind, R is not this. That's what I was trying to show. When you do R here, R is this because this is technically right here. We just put it there in order to draw the component, right? But really, we can move this vector anywhere just as long as we don't change the direction, right? But we know that that vector sits right here. I'm doing too many greens. Let me do that in the red. This vector, I'm just going to redraw it right here because that's where it actually sits, right? So the R would be this, and this would be the perpendicular force, right? This is F sine theta right here, right? This and this are the same thing. Remember, you can do that. If you don't remember that, go watch the component video that I made for you that shows you how to get components of things, and I do that in there. We can move this around however we want, okay? So I'm just bringing it over here. So the R would be this R1, and then the perpendicular component of force is F sine theta, so that would go in there. You've got to know how to do that. You will be tested on that. Okay, how to do that method. So rewind that if you don't understand what I just said, okay? But remember, get the components of force. Find the component of force that's perpendicular to the surface area. That's what's going to take the place of the force here. So then you just write the equation by getting your sign first. Write R, whatever R is, the distance to that force, and then write the value of that component. Remember, sometimes it can be F cosine theta based off where the angle's at, right? If this angle was up here, this would be F cosine theta, right? That's what I'm saying. All right, so now finding torque using the lever arm, right? So this is finding torque using the perpendicular force, or using the mathematical definition of torque. This is finding torque using the lever arm. This is typically what we're going to want you to use when a force is at an angle. Okay, here, right, we use the component of, even though this force was applied at an angle. I know it's hard to see now, but remember that force was applied at an angle right there, right? That was the original force there. You can find it this way, the torque, right? Or you can find it this way, and this is what we would prefer, okay? But keep in mind, you gotta know both methods. You gotta know how to do this one too, okay? So, finding torque using a lever arm, the first thing you have to do is locate force, axis of rotation, and the angle. Okay, so we know right here, this is the force, it's unlabeled. This is the force, right? We know that's the angle and that's the axis of rotation. Okay, cool, we did that. The next thing to do, right? Some people say this for the end, but don't. You will forget to get the sign of torque. So get it right away, okay? So how can you do that? What you do is you get your pencil or your pen or whatever you have, place it on the plane of the object that we have, hold it very lightly at the axis of rotation so this thing can move, and apply the force. So even though this is at an angle, yeah, directly down, it's easy to see, but just apply it at an angle and look what it's going to do. So this thing's going to spin counterclockwise, right? It's going to spin clockwise, right? I know the way a clock works. Clocks spin this way, right? This is going to spin clockwise. This force is going to make this spin clockwise. So clockwise is a negative sign. We give things, when the object's going to spin in a negative direction, we give torque a negative sign. if the force were to spin the object counterclockwise, which is the opposite way of this one, then we would give torque a positive sign. So the first thing you do is locate those things. Okay, the next thing you do is just write that. Say negative torque equals, and then stop there. Okay, that's what I mean by that. Locate force, get the sign. So you're just going to write that. Negative torque. Right? It's going to go clockwise. This force is going to make it go clockwise, so we know the sign's negative. Okay. Sometimes it'll be positive. We'll talk about it over here. Okay, but here it's negative because of the direction. Next thing you do is find the lever arm. Okay. Now keep in mind, if the force is not at an angle, you don't need to do all this. You can just use this equation because F will be F, R will be R. There's no angle there, right? But if the force is at an angle, you got to go through this process, okay? So, next thing is finding a lever arm, right? That's the next step after getting the sign for torque. So how do we do that? Well, that's these steps over here, right? So the first thing we do is kind of the first step that we did over here. Locate axis of rotation. There it is, right? Locate force. There it is, right? And locate angle. Okay, we've done that. Everything. Okay. I think I just made it worse. Okay, so this is R, right? So we located everything. Next thing is draw the line of action. The line of action is the line that's going to go through the force. It's just extending out the force vector. Okay, it's a line that's drawn directly through the force vector. You just extend it out. This purple dotted line, they have going all the way down here. See how long it is? That's my line of action, and you want to label it. So draw the line of action and label it, okay? Next thing you want to do is draw the lever arm. Now the definition of the lever arm is the shortest distance from axis of rotation to the line of action, okay? That's the definition. But how you should do it is a different story, okay? So the best thing to do, I'm going to erase it here real quick so you can see what to do. The best thing to do is to make a 90-degree angle with your line of action. So this is our line of action, right? So make a 90-degree angle. And what you want to do is then bring that line closer and closer until, because we see that's a 90-degree angle, but we see that it's not going to what? Make it to the axis of rotation. So we want to bring that closer until we know that it's at that point where it's going to not just make a 90-degree angle. Make sure I do that right. Not just make a 90-degree angle with this, but also go to the line or to the axis of rotation, okay? This line I just shot, you saw how I did it. I made the 90-degree angle with the line of action, and then I drew lines, right? You can do multiple lines until you find where it's going to go up to the axis of rotation, and you can complete the line to the axis of rotation, and that's what this is saying. Okay, so make 90 degree with line of action, complete line to axes. Alright, and then that line right there is going to be L, or your lever arm. Alright, so that's how you find the lever arm. Once you find the lever arm, you want to write the equation for the lever arm here, right? And we write the equation for the lever arm in terms of R. Now, the reason why it's important that this isn't a right angle, by the way, is because we have formed a right triangle where R is the hypotenuse. And that makes it very easy to write the lever arm. That's what we're doing here. See this right triangle here? There's a right triangle here. R is the hypotenuse. So what we do is we write the lever arm in terms of the hypotenuse and angle. Right? So we see the lever arm's opposite, right? So that's sine theta, so that's R sine theta. Okay, because we know it's going to be in terms of opposite. If you don't know that, you should know where that's coming from. Okay, it's really, really, really important that you know where that's coming from. If you don't, I can do it for you right here, right? So we know that sine theta for this problem, for this specific one, right? You know, sine is going to be equal to opposite over hypotenuse, right? Opposite is going to be the lever arm. The hypotenuse is going to be R. If we want to solve this for the lever arm, we bring R up to sine theta, so we see R sine theta is equal to lever arm. Okay, so that's where this is coming from, but you should be able to just see that now. You shouldn't have to go through those steps. But right? So this could be cosine 2 based off the angle, right? It's not always r sine theta. It's just r sine theta because of where L sits. Once you find the lever arm, then you can write the torque equation, okay? So then you can start and say, okay, we got the sine first, so we already had that written. Remember? We had this written already, okay? The next thing you do is write the equation. So when the force is at an angle, right, and you're using the lever arm, you start with this, you write FL, and then you want to fill in L with the lever arm you have. So here's the full equation right here, right, where we see that torque, the torque equation, that the sign's negative, and we see that it's equal to FR sine theta. Okay, so that would be how much torque that force is going to apply to this object, or what does that mean? Remember, you gotta know what that means. How effective that force, this is how effective that force is going to be in spinning this object, right? When we say that's how much torque it has, make sure you understand that. Okay, so that's just how to do the pieces, but why do we need to know to get the pieces of torque? Because we need to know how to net torque. And not only do we need to know how to net torque, but we got to be able to use torque in our Newton laws. We're going to be given new Newton laws that we have to know how to use. Okay? So, how do we net torque? First of all, you've just seen me solve for torque a lot of different ways over here. Right? We don't want you getting confused and saying, well, now which way do I solve for? Which one of those ways do I use to solve for torque when I'm going to sum them? You just gave me a lot of different ways. So, this is what you do. When you're going to sum them, when you're just going to add them together like this, okay? We want you to use these two combinations. If the force is at 90 degrees or perpendicular to the surface, right? When the force is 90 degrees or perpendicular to the surface, that's what that means. We want you to use the equation of torque equals to RF, right? This one. Use that equation to describe, that's what we're doing right here, any force that's perpendicular. That's how you want to write the equation for it, okay? That's what you're going to stick with every time when you're going to sum them. Talk about it here, okay? If the force is at an angle, then you want to use the method we use down here. You want to write the equation in terms of the lever arm, okay? And where L, right, torque is equal to FL, where L can either be r sine theta or r cosine theta, okay? So these are the two things. If the force is perpendicular, you're going to write your torque equation and sum the torques using this equation. And if the force is at an angle, you're going to use that equation to sum your torques using the torque is equal to force times the lever arm. Okay, when the force is being applied to angle, we're going to see how that works right here. Okay, so that's important to know. That's when we're netting torque. You got to know how to do all these methods. You have to know each well, really it's just these methods right here, right? You got to know these methods. You got to know all the methods, right? This is one where it's just looking at the perpendicular force. So here's one method to get torque, right? Where if the force is perpendicular, we can just use that, which is what we're saying over there, right? Here's another method to get torque right here. We're finding torque using the perpendicular force component. Here's another method to get torque using the lever arm, okay? So when you're going to sum them, if it's going to be at 90 degrees, just use this method for the 90 degree or the perpendicular forces. And when the force is at an angle, use this method, the lever arm method, okay? So we have a situation here. I'm not going to solve this for you. In fact, there's another video that you can watch that does this problem for you step by step. But we can see some things. I just want you to see how to use this stuff, right? So to net torque, the first thing you want to do is get all the separate equations for each force. Get the torque equations for each separate force. And then set up your sum equation. That's the steps to this, right? So we know F1, we kind of know some things, right? F1's what? Being applied to the axes of rotation, which means what? There's no torque there. So T1, right? F1 is going to be T1. It's going to be 0 because of the concept. It's applied to the axis of rotation. R is 0, torque is 0. All right, what about 2? Well, we know that the first thing to do when we're writing our torque equation, right? So this is how to find torque using the lever arm, and this is also just how to find torque in general. Always locate the force axis of rotation and angle, and always get the sign first, no matter if you're using this method or this one, okay? So here, right, we see F2, we just want to see the way it's spinning. F's going to make this thing spin clockwise, which means it's negative, right? And then since it's perpendicular, we're going to use this torque to write the equation for it. So it's going to be, right, the distance, which is R, or R2, we're going to call it for F2, R2, right? And then the force perpendicular is just F2. That thing's totally perpendicular, right? So we can just keep it like this. So the sign is there, and our equation's there. All right, and since it's 90 degrees to the surface, we're using this torque equation to write that, okay? Now, F3, well, we just did F3 down here. You gotta go through all these steps to get this equation, right? But we know once we went through all these steps and found the lever arm is equal to r sine theta, we knew the sign was negative because we said that this was gonna rotate this negatively, counter or clockwise, just like this is rotating, right? This is the same thing, right? So we know that the sign's going to be negative, and then we know since it's at an angle, we want to use this form, right? Where it's the force times the lever arm, where we write F first, right? That should be F3, by the way. And then R3 sine theta, right? The L is either going to be r sine theta or r cosine theta. We know it's r sine theta because it's opposite of the angle. We talked about that already, right? So that's going to be the torque equation for that force, right? And then for 4, it's perpendicular, but we can see that it's going to make this object want to spin counterclockwise, which is positive. We should have wrote that there, right? So torque is positive for F4, but it's also perpendicular, so we just have to use this force, so it's going to be R4, F4, okay? Once you have all your equations, you can make your net equation. You can sum all your torques together. Now, I like my equations to start with positive numbers. So I started with R4, F4. You don't have to, though. You can start with one of these torques, right? We know torque 1's 0, so the only 3 torques that are doing anything, or the only forces that are providing torque to this object is F2, F3, and F4. So only torque 2, torque 3, and torque 4 are going to be in this equation, right? So I start with 4 because it's positive, R4, F4, I just write it in there. And then I do the next one, I take the sign, right? So for T2, sorry about that. Oh no, that is 3. So for T3, I just went with that one next because it was right there. You could have really done either one. So for T3, it's negative, so I gotta write the negative sign there, right? Even though summing them's adding them, right? That's why this sign's important. So since torque is negative, we gotta put it in this equation. So this one was positive, it stayed positive. This is negative, so we gotta represent it as negative and put that equation in there, right? And then T2 is also negative, or torque 2, sorry, is also negative, right? So we write that there, and then we write the equation R2F2. So that's the equation to sum the torques. And if these were numbers, you would, right, subtract these 2 from that one, and you'd have a number, and you know the net torque on this object due to all those forces. But what are we saying there? You know how effective all those forces combined are going to be at spinning that object. That's what we're saying. Don't forget that, okay? Now, how does torque relate to Newton laws, all right? Once you know how to sum the forces, you know that on either Newton law, just like when we did regular Newton laws, these just fill in with this. This part is this, and this part goes in here. So this can go right in here and make it equal to 0, or this can go right in here and make it equal to I alpha. Okay, so when do we know that? All right, well, this is what's important here, is that we start from this point on to look at objects all together. All their motion, their linear motion, or what we say their translational motion, and their rotational motion, okay? Because I can have them like this marker, right? It can fall. It's going to start at rest and then speed up as it falls, right? It's not in translational equilibrium because it's speeding up, but it is in rotational equilibrium because it's not spinning. But if I get this thing and spin it and let it fall, now it's not in rotational or translational equilibrium, okay? So we have to start looking at that. Is the object just moving in linearly, or is it spinning and, right? Because this is moving linearly. The marker's moving up and down, but it's also spinning, right? That's super, 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 super crucial, okay? So, what's important about understanding this then is just to understand that you apply it the same way that you did to the Newton laws, right? So when we say that the sum of torques are equal to 0, that's the Newton law, Newton's first law for torque. Just like we said for Newton's first law when we summed the forces for translational equilibrium, right? It means the same thing for torque. That's the connection you need to make here. Sorry, I said that a little weird, I think, right? So just that's how we start to look at this, okay? When we start to look at objects, we want to say, is it in translational equilibrium, right? Is it not moving, or is it moving at a constant velocity? And is it in rotational equilibrium? Is it not spinning or spinning at a constant velocity, okay? That's how we dictate that. That's how we recognize that. So every time you look at an object, you go, okay, is that object in translational equilibrium? Well, you ask yourself, is it standing still or moving at a constant velocity? And then you say, is it in rotational equilibrium? And you say, I don't know, is it not spinning or is it spinning at a constant velocity? That's how you know if it's in equilibrium, translational and rotational, okay? So again, sum of torques are equal to 0, or you're in rotational equilibrium when you're not spinning or spinning at a constant velocity. You're in translational equilibrium, right, when you're not moving or you're moving at a constant velocity. So translational is your linear motion, rotational is your spin, right? And things can roll, like something rolls, right? When something rolls, like a disc, like right about here, it has both rotational and translational motion. So you're going to have to think about these things together depending on what the object's doing. The object's rolling. I think you can see this from there. I think you can see the table. If not, then that was worthless. But that's rolling, right? It has linear motion. I wrote it on my hand. Something rolls, right? It has linear motion and it has rotational. It's spinning, but it's also just moving straight, right? That's what we're saying. So you're going to have to combine these. So you know things, this is important. You know things are in equilibrium. How? When either it's not moving or it's moving at a constant speed, right? And that's for both of these. So for rotational equilibrium, it's either not spinning or spinning at a constant omega. For translational equilibrium, it's either not moving or moving at a constant velocity, okay? So you use this when the object is not spinning or moving at a constant velocity. Like if it's a ladder sitting against the wall, that thing's in rotational equilibrium. It's not spinning, it's leaning against the wall. So you can use this for that situation, okay? But what if something is spinning? Not just spinning, right? Because it can be spinning here, but spinning faster and faster, like getting faster and faster, or slowing down. It's spinning, but its spin is slowing, slow to a stop, right? So that's when the spin is changing speed. Well, we know then that there's going to be some sort of net force here. So we have before discussed net force in terms of Newton's second law, right? Where we said the sum of forces are equal to the rate of change in motion of an object, right? The net force, write that in there, is equal to the rate of change in motion of an object, right? And we knew there was net force when something was speeding up, slowing down, or changing direction. It says V changing, right? But that's how we knew there was net force, right? Is when it was speeding up, slowing down, or changing direction. Well, to use Newton's second law in terms of torque, we do the same thing, but we just look at alpha. So if there's some net torque on an object, right, this is going to be torque net torque, either the thing's going to be speeding, start to spin faster and faster and faster and faster and faster, or it's going to be slowing down, right? It's going to spin slower and slower and slower and slower, right? So either speeding up in terms of spin or slowing down in terms of spin. That's how you know there's some sort of net torque on an object, and that's how you know you're going to use this equation here, which is Newton's second law for torque. But it works the same way as Newton's second law did when we were talking about translational motion. So that's Newton's second law for translational motion. This is Newton's second law for rotational motion, okay? It's used just the same as this. You're going to sum the torques and put it in this side and finish the equation with that, right? Where I is your rotational inertia, we'll talk about this in a different video. So I have a video for rotational inertia where we'll talk about this, okay? And alpha is a new term that we're adding to you, but that's just angular acceleration. So it's equivalent to this A over here. This is the rate of change in motion in terms of your translational speed. This is your rate of change in motion in terms of your circular speed. Okay, so alpha works just like acceleration over here. Acceleration was the rate of change in motion, right? This is the rate of change in motion as well. This is just the rate of change in motion in terms of your translational motion or your linear motion. This is your rate of change in motion in terms of alpha. Okay? Super, super, super important to understand. Okay? So, what's important about knowing all this? Well, once we can see the amount of torque that's being applied to an object, or how effective forces are going to be in spinning an object, we can see how the object's going to move using angular kinematics. Okay, that's super, super important. So these kinematics, just like your translational kinematics or your linear kinematics, work exactly the same. You can only use these kinematics when alpha is constant, okay? When angular acceleration is constant, you can use these kinematics to solve for the motion, the rotational motion of the object. How long it took it to get to a certain speed, right? The rate of change in motion in terms of speed, how fast it was initially moving, or its displacement. Remember, displacement is theta in terms of rotational motion. Also, don't forget, and if you need to go back and watch the rotational motion video, you should, omegas in radians. So when you're getting values over here, omegas in radians, thetas in radians over here. Okay, so remember how you know how to play with those, okay? But the point is that you can connect Newton's second law to these equations just like you connected Newton's second law for translational motion to your linear kinematics. So you want to, if you can find out if acceleration is constant by finding out if the torque is constant, then you can solve this equation for alpha, put it into one of these equations and find out how fast it's going, or find out its displacement. Okay? So you want to use these together. There's a video solving some problems with these. I don't do it here because these are just the concepts. But you have to know that that's how these are connected. So you want to know how to get the torque, know how to sum the torque, know what Newton law is going to apply to the object, because once we start applying these to real objects, right, is it a ladder leaning against a wall where it's in equilibrium, or is it like a centrifuge that starts at zero and starts to spin faster and faster, right? That centrifuge has torque, and we can find out how fast it's going to spin by finding out the torque, right? Or we can find out how fast something's going to spin in terms of if a rope, like an elevator, is attached to it with a rope, right? That thing's going to start from rest and spin and get faster and faster as it pulls the elevator up, right? We can look at all that stuff by first finding out the torque, summing the torque, applying it to a Newton law, whether the thing's in equilibrium or having some sort of rate of change in motion, and then use that to solve the motion of that object in terms of its spin. Okay, there's a lot going on here. Plus, there's still rotational energy that's on another video that you need to understand, okay? So, just some last things here that I think are important. First thing that's important that I don't have up here that I should write is center of mass. Center of mass. What is center of mass? What is center of mass? I'm going to talk about it, okay? Center of mass is where all the mass of an object is located, is directed, right? So right there, that's the center of mass of these markers. How do I know? Because I can balance the object there. Wherever we can balance the object is where the center of mass is. It's where all the mass is being directed. You might say like, well, what are you talking about, Carl? How do you know that? Well, if the mass was being directed out here or out here, right? If it was distributed everywhere, I would have to hold the marker like this to balance it. But since all the mass is distributed to one, ooh, got some torque there, huh? Ooh, it's getting torque. Torque went away. See that? When I hold it right there, that's where all the mass is directed, and that's its center of mass. Why is that important, though? Why is center of mass important? Well, center of mass is where the object naturally is going to rotate. So this marker has a center of mass right there, right? And when I spin it, it's going to naturally spin. You see that? I don't know if you can see that, but it's going to naturally spin around that point, right? We said it's right there. that point, right? So right there, that's where this thing should be spinning around. Watch. I don't know if you can see that, but it is. It's spinning right here around that point. Okay? So center of mass is important because it's where all the mass of the object is directed, and it's where the object will it's the point that the object will naturally spin around. Okay? Every object has a center of mass. Okay? If it has weight, it has a center of mass, and based off of how the mass is distributed, is going to dictate where the center of mass is. It's not always directly in the center. Like if I have an object like this with no mass on it, the center of mass is going to be right in the center. This is where the center of mass would be. But if I put some very heavy object here, the center of mass is going to shift towards the center, towards the heavier object. So even though when I had this board here without the object on it, the center of mass is right in the center. When I add that, the center of mass is going to shift towards the larger object, so it won't be directly in the middle. So this will be the new center of mass with the object there. But if I get rid of that object, the center of mass moves back to the center of that plane. So that's how center of mass works. But just keep in mind, all objects have center of mass. We're going to use center of mass in all of torque because that's where things naturally spin, right? So it's going to be a place. Center of mass for all objects is a place where force is applied to the object that can give it torque, right? This thing has, if I don't balance it on the center of mass, it's going to get torque. It's going to pull itself down, right? Because the center of mass, it's going to want to rotate it because its weight is pulling on it. It gives it torque. So that's why center of mass is important. You'll see in the videos that we solve things, it's going to be very important. But just know what the center of mass is. It's where all the mass is located or centered for an object, and it's where an object naturally will rotate. If you have to build a lever system, right, you want to build some fulcrum, you want to put the fulcrum at the center of mass because that's going to make your system here easier to lift. All right. Another thing to look at is torque between two spinning objects, right? So this is a hoop, right? A hoop is hollow. This is a hoop. This is a disc, right? Discs are solid all the way through, a solid disc. This is a hollow hoop. There's nothing in here, it's just hollow. All the mass for the hoop is directed all the way out here, where for the disc, right, this disc has one weight to it, but that weight's distributed all along that plane. All right, so what we see is that with the hoop, all the force is what? Furthest from the axis of rotation. Where here for a disc, the force is very close to the axis of rotation and very far. So what happens when you end up adding all these is that the force, since it's being distributed all the way along the plane, it gives way to less torque. Okay, because, right, the force that ends up being out here isn't all the net force. These forces all added together is going to be equal to the net force, right? So this force that's furthest from the axis of rotation isn't F net, it's just F3. But when we add all these forces together, we get F net. Or with a hoop, F net is, we don't add a bunch of forces together to get F net. The whole F net is directed out here. All the weight of the hoop, right? All the mass of the hoop is directed towards the outside, where all the mass of the disc is directed everywhere in between. So because of that, we can talk about torque here. Since this is furthest away from axis of rotation, that means it's going to take you're going to have to put a lot of force, a lot of torque to start to spin this. It's going to be hard to spin, and it's going to be hard to stop spinning, because when you have to stop it, you're going to have to put a lot of torque into it, because the force when it's spinning is going to be so efficient that you're going to have to, it's going to be hard to stop. Okay, so here, right, it takes a large torque to start to spin a hoop, and it takes a large torque to stop spinning a hoop, because all of its mass is directed furthest from its axis of rotation. So you have to apply a large torque to this to stop it, and you have to apply a large torque to it to start to spin. And when it's spinning on its own, it has a large torque because all of that mass is directed furthest from axis of rotation. Versus the disc, when it's spinning, it takes less torque. It takes a very small torque to get it to move. So you'll walk over and just start spinning it. right? And it also takes a very small torque to stop it, because you just have to apply a very small force to get it to spin. And if it's spinning, it's not going to have very much torque, so you have to apply torque in the opposite, a very small amount of torque in the opposite direction to get it to stop. Okay, and that's just because of the way the forces are distributed, right? We know that max torque is when all the force, the F net, is distributed furthest from the axis of rotation. Here, F net is distributed all the way through, where F net is all the way here at the end, so this will have the most torque, the hoop, versus the disc, okay? And again, same thing here, right? F1 gives an objectless, so when we look at these two forces, since this is closest to the axis of rotation, we can say F1 is going to give less torque than F2, right? And what does that mean? That means F1 isn't going to spin this object as well as F2 will. Okay, so hopefully that made sense. Go back and re-listen to what I said there, because this part's kind of important to understand, right? Why hoop's spinning the way it is, why disc is spinning it is, why the torque is what it is, right? Again, I want to say it one more time, that all the mass of the disc is associated all the way on the end, right? For all the for a hoop, all the mass is all the way out the end. For a disc, the mass is distributed all the way through, so the F net isn't as strong at furthest from the axis of rotation as it is for a hoop, and that gives way to this torque, okay? So don't forget about that, center of mass, everything we talked about. Go back, rewatch this, rewind, listen to it again and again, because this is really, really important stuff. Don't forget all the methods you have to know, all right? But I'm super proud of you. You have made it to the middle of the semester, and I am proud of you. I don't care what your grade is right now, because grades are kind of silly, I'll be honest with you. But you're working hard, and that's what's important. And I hope you're proud of yourself, and I hope someone out there's telling you they're proud of you. And if they're not, you need to know that there's someone is, if you were to ever meet me, if I don't ever meet you, but we were happen to cross paths, say, Carl, I watched your video, you know I'd be proud of you. Okay? So take that confidence, have confidence in yourself, reach your goal. Don't let physics hold you back, okay? Reach your goal for me. If you're like, oh, Carl, I want to thank you because all these videos are so helpful. Thank me for reaching your goal. Go change the world for me. Make this place better, because all of you are so special. I get so excited from you students because you're all so special. So go change the world for me, all right? I'm super proud of you, and I'll see you on the next video.